Hello, my name is Ashish, and I'm going to present today on the topic of importance of association techniques used in bioinformatics. All the papers I've chosen are from PubMed, which is US National Library of Medicine, National Institute of Health. This is because I've done my master's in bioinformatics, and I think data mining is very important to extract data, and I've used PubMed before. In this case, the equation can be conveniently modified to calculate H confidence P1, P2 by making the following substitutions: NP1, which implies the sum of weights of edges on P1, similarly for the P2. And in the paper 2, I've chosen the topic of discovering protein DNA binding sequence patterns using association rule mining. Protein DNA binding plays a central role, a very important role in genetic activities such as transcription, translation, packaging, rearrangement. There's a lot of things that goes on when a protein binds to a DNA, and each protein is specific to a DNA. Therefore, it is very important to identify and understand the protein DNA bindings. There are many data mining techniques such as the neural networks, support vector machines, SVMs, and regression, which generate rules which are not so trivial to interpret. Furthermore, many data mining approaches are based on specific families or particular datasets where the generality of the results are limited. In this case, we use the association rule mining to discover associated TF, TFBS. TF is the transcription factors that are used in the DNA to make a DNA strand, and TFBS is the transcription factor base sequences, which is a sequence pattern that builds the transcription factors. On the other hand, sequences serve as the most handy primary data that can carry important information for protein DNA bindings. To formulate the TFBS pattern sequence discovery problem into association rule mining, we have to perform the protein DNA binding records into formats of item sets. The item sets are the k-mers, and the confidence formula is given here for two of the association pairs. The first as a support for the k-mer DNA. The k-mer is a component of DNA intersection, the k-mer AA, that's the amino acid, divided by the support, and the same is given for the reverse confidence, wherein the first formula is for the forward confidence and the second one is for the backward confidence, and the support X is the support of the item set X. For example, there are 70 TF5-mer and there's 70 TFBS pairs without any further removal in the N column. That's in the table 2 with both forward and backward confidence, which has a value of 0.5. And here's the flowchart for the proposed framework to discover association rules from the TransFact database. The TransFact database is the transcription factors database from which the transcription factors of different DNA components has been taken. Now here it shows the process of the transcription factors. The transcription factors TBFS sequence pattern that has been used as a transaction table with binary data with 0 and 1s, and it has been uploaded with the a priori algorithm, and pairs has been seen here, whereas the TF k-mer pair 1, pair 2, pair 3, and there are 1 to m pairs, and then the rescanning has been done to get the association rules with different confidence levels ranging from 0.5 to 0.9, and table 2 shows the quantitative measures for the different pairs across different confidence levels ranging from 0.0 to 1. So these are the number of rules that has been discovered, shown in the table 2. In the paper 3, the topic I've chosen is the cross-ontology multi-level association rule mining in the gene ontology. So starting with what gene ontology is it's the standard platform for describing characteristics of gene products. Gene products includes different components like the biomarkers, gene tables, and etc. A lot of them. So in the current discussion, we address each transaction corresponds to a gene product and their attributes that represent the presence or absence of a particular gene ontology annotation. So this is very much important, and three sub-ontologies of the gene ontology exhibit different distributions of terms across levels of abstraction in the structure of gene ontology, and these have been assigned in annotations to different data sets. So here gives the multi-level association rule mining. Starting from it gives the this is a bottom top approach. So it starts from the bottom. The gene ontology product number has been given at bottom, and it all the way goes to the top. And here we can see that there are 1 2 3 4 5 6 7 8 levels, and this is called the cross ontology level by level algorithm. And the advantage of this algorithm, as seen here, that the multi-level rule mining has the potential to overcome the specificity and information content issued by the mining at multiple levels of the gene ontology instead of just focusing on a single level of detail. In what we see in the general association rule mining, it's just the single level of mining, but in the cross ontology level by level, it starts from the bottom and goes all the way through the top, and it has got different clusters and mining patterns that gives a very useful information and meaningful information going forward. This is a chicken mouse dataset that has been used with the support of 0.05% and 60% confidence, and the p-value is also given 0.01. The p-value can be compared finally to the significance value, which is 0.05. Here we can see the number of rules mined using the two different algorithms. The first is the COLL that we have seen before. That's the cross ontology level by level, and there's one more that has been compared to, that is the Burgun BURGUN algorithm. So different rules have been mined. The first one, 17, it's more than 1 lakh. So the same has been used in the Burgun algorithm, and these have been compared, and it was seen that the first one, the cross ontology level by level algorithm, has been much useful and gives much meaningful patterns compared to the Burgun algorithm. In the paper 4, fuzzy association rules for biological data analysis, a case study on the yeast. Yeast has been always a topic of interest because there are several unknown data patterns that has not been discovered yet. So let's start with what fuzzy set theory is. The fuzzy set theory allows an object to partially belong to a set with a membership degree between 0 and 1. So it's a binary data. Likewise, fuzzy logic allows a statement to be true with a certainty degree between 0 and 1. So it gives a value between 0 and 1 that signifies the importance of that particular data. So the primary goal in this paper is to present novel fuzzy association rule extraction method based on the top-down frequent parent growth. The previous one was the bottom up, and this is a top-down approach. As we can see here, this gives different variables with different confidence levels and support values, and the final variable, that's the FTR, that has been given. I'll explain it later what that is. So the certainty factors, confidence and support thresholds were varied in each study to obtain a number of rules which could be easily analyzed by the expert. The threshold values and the total number of rules obtained in each experiment are detailed in the table. The estimated number of false rules was calculated as the mean of the number of rules obtained from each of these 100 randomized datasets. In this way, the FDR, the last column, FDR, the false discovery rate, allows us to check the quantity of the rule sets. So this has been used as a parameter to see the quality of the dataset or the rule sets. So since the FDRs obtained are very low, we can argue that very few rules were generated by chance, that is by randomness, and that the majority of the rules obtained represent real biological association, proving the significance of the methodology. I've seen in the paper that they have actually compared the FDR results to the actual results in the lab, and they found that the majority of the rules obtained represent a real biological association that which actually implements that it has a significance value. In the paper 5 and 6, I've combined both the papers: mining association rules among gene functions in clusters of similar gene expression maps, dynamic association rules for gene expression data analysis. So here the modified version of association rule has been used, that is the dynamic association rule, which gives a causality between genes and phenotypes, which is a very important relationship in the biological data. And in here, DAR algorithm has been used to preserve the causality of the relationship between genes and symptoms. So here is the flowchart of how the rules have been found. First, the dataset has been normalized, and then the discretion has been done, and an association rules with minimum support and minimum confidence has been used. That is from, I guess, 10 to 90%, and meaningful rules have been extracted, and the ambiguous rules that doesn't play an important role have been taken out, and final rules have been uh, jotted down. So with the dynamic support and confidence, it gives the number of meaningful rules to be 14, that we can see here, the meaningful rules, which can be found when the cutoff points were set to be support equal to 30 and confidence equal to 85%. The number of final significant genes, that is very much useful in building a relationship between the symptoms and the symptoms and the DNA and the gene expression, has found to be 9. And the table 2 shows the gene expression level of HDL deficient mice, and which had a significant differences in 14 sequence tags, STCs. So the main statistical techniques currently used are multiple t-test, factor analysis, principal component analysis, and other dimension reduction methods. So here we can see the association rules from gene A to the case and the control, with using different confidence levels from 70 to 90%. So these are the confidence and the number of rules that has been generated using a primary software. So these are my references, all the 6 papers that I've used from the PubMed. Thank you so much.